Hello and welcome to the 7th Long Products webinar. I'm Ken Landau, staff engineer at AIST. This webinar will feature performance-based reheat furnaces. Whoops, I should start it. Here we go. As with all AIST functions, I'd first like to go through the antitrust compliance guidelines. Do not discuss with others your own or competitors' pricing procedures, or anything that might affect prices such as costs, discounts, terms of sale, or profit margins, or anticipated wage rates. Do not make statements about your own pricing or those of competitors, and do not talk about what individual companies plan to do in particular markets or with particular customers. AIST also has anti-harassment policies, and those are listed there. Now the things to know. The attendee audio has been disabled, as has the video. Any questions for the presenters, please use the Q&A feature that is on. If you move your mouse to the bottom of the screen, you'll see a Q&A icon there. Again, please use that function. It gets logged in and makes it a lot easier to, the presenters can also answer either verbally or right in that system, so everybody can see it. The host and the moderator will determine which questions are presented to the presenter. That will be towards the end, or that will be after the presentation. And the session is being recorded and will be available for on-demand replay on our website, aist.org. If you have any technical questions, please send an email to training@aist.org. For photos and recordings of this presentation is not prohibited, so do not make any photos or recordings. You'll be given a link to access the presenter contact information in the recordings following the end of this webinar. I'd like to introduce Bridget Darby. She is our moderator today. Bridget has a bachelor's degree in promotional communications and international business from Cleveland State University. She's been working in the steel industry since 2011 and a member of AIST since 2012. Bridget has been involved with the Long Products Technology Committee since 2012 as an active member, as well as serving the committee as the AIST staff representative from 2015 to 2017. After leaving AIST, she held a sales position for a leading laser measurement company, followed by an outside sales position for a leading OEM. Now, with that, Bridget, I'll let you take it from here.
Good morning. I'm going to introduce the presenters here. We've got Bill Lucas, the technical sales engineer. Bill has a mechanical engineering degree from Kent State University. He has 37 years experience in the design and development of industrial furnaces. He started his career with the electric furnace company, serving as draftsman, application engineer, project manager, and project engineer, and then as an engineering manager for the Canadian subsidiary. Then he joined Ebner Furnace Company, supporting their continuous furnace development steel. Lucas has been with Phoebes for more than 2 years, supporting the Phoebes Steel division, focusing on thermal processing equipment. We've got Mathieu Herbert. He holds a master's degree in engineering from Polytech Lille. He has been with Phoebes Stein for 13 years. He started as a commissioning site manager for new reheat furnaces, continuous annealing, and continuous galvanizing lines. He is now working as a service engineer. Herbert visits customers all over the world to help them improve profitability of their existing furnace with process audits, revamp opportunities, providing operational expertise, and by obtaining immediate improvements. Thierry Robbins holds a doctorate in physics and material chemistry. He has been with Fives Stein for 15 years, initially as a furnace level 2 engineer. He has been involved in the design and commissioning of process control and in digital solutions globally. He currently serves as a sales manager for process control software and digital solutions. Thierry has published several articles in the area of ceramics for nuclear waste confinement for a new generation of fuel cells and various articles addressing Fives Stein digital solutions. And finally, we have Brenda Chan. Brenda holds a Master's of Advanced Studies in Thermoregulation with the University of Paris and with the Paris Mining School. She has been with Fives Stein for 14 years, serving as a research and development engineer. She has led R&D projects addressing energy efficiency improvements for reheat furnaces and is managing the development of oxide scale growth. Oxide scale growth control, holding 2 patents. Chan has been responsible for the design and sizing of several reheat furnaces. In addition to new reheat furnace installation, she has provided various energy and process audits globally. And we'll get started with Bill here.
Okay. Thank you, Bridget, and thank you today's participants for joining us in this AIST webinar. We appreciate your time and we hope you find it interesting. Next. So we're going to discuss performance-based contract solutions for reheat furnaces. This is a long title, and I'm going to break this into 2. I'm going to cover with a few slides the performance-based contract. I'll leave the solutions for reheat furnaces, the more interesting part, for my colleagues. So what's the definition of a performance-based contract? Performance-based contract is an agreement between a supplier and the user. It's based on evaluation of current operating conditions. This could be the cost of operation and what's being produced with these costs. Providing recommendations to improve performance and reduce operating costs. There are several areas that can be addressed here. Then estimate savings when implementing recommendation. Okay, it's depending on what's observed early on, it's possible to provide an educated guess of what the savings may be. Implement methods to measure savings achieved. There are several potential areas, and each of those we have to be able to measure the change. And sharing of the savings between the supplier and the user based on success. Again, going back to the early evaluation and working with the estimate, it is possible to come up with potential savings. We develop a mutual agreement on how we could distribute the savings between us. This allows continued improvements without putting out money until savings are realized. And finally, we finish up with the completion of the agreement and closure of the contract. Of course, we hope that working together continues after that, but there is an end to this, and then we're looking for win-win opportunities. So the goals. The fundamental goal is to achieve savings and improve operations. We want to optimize availability, increase throughput, maybe it's improved quality, reduce fuel consumption, reduce emissions, or reduce scale. These are goals that many of the producers would like to achieve. So we've implemented a 5-step approach to achieve the goals. We're going to read the bullet points off here. Step 1, preparation. Utilize remote communication in order to evaluate the yearly cost for each benchmark and define a baseline test product mix. Step 2, a baseline and immediate improvements. Here we're on site and we implement a baseline performance test and we apply some immediate corrective actions where we can start to achieve some savings. Step 3, midterm actions. Here we implement longer duration actions, again on site, but this might be replacement of long lead items that were found to be needing replacement, or implementing an improvement that required some engineering. With the furnace working well, step 4, a furnace mathematical model. Here we're trying to improve the control of the furnace on a higher level. And then step 5, long-term improvements. In this case, we'd like to cover a scale reduction system. So the goals for each step will be covered in more detail. My colleagues will go over these steps and what they may accomplish during each step of the process. The first 3 goals will be covered by Mathieu Herbert, the mathematical model, of course, Thierry Robbins, and then the scale reduction by Brenda Chan. With this, I will turn it over to Mathieu Herbert.
Thanks, Bill. Hello, everybody. So the 5-step performance-based project is not a new product. It's not a new technology, but it's a different approach for project management for Reheat furnaces improvement. We will see through this presentation different advantages of managing the project this way, but one of the most important advantages is to have a clear dashboard, detailed dashboard showing all improvements reached after each step for each of the criteria that will be evaluated. To generate the dashboard, there is a very important step, that is the first step, which is called preparation. During this step, we will evaluate costs of each benchmark and define the baseline product mix. Jointly, the project manager of the steelmaker and any partner will evaluate for each cost, basically how much saving we can get for each % of improvement on fuel consumption, scale generation, product throughput, quality, emissions, and product availability. This starts as soon as the contract is agreed, and with remote communication, we exchange all the data necessary. 2 examples, just easy examples out of this. For the consumption, we will consider for a production based on 2 or 3 years of production, long-term production, how much money was spent on the gas, and we can deduce how much saving we will get for each % of fuel consumption optimization. Another example that is interesting is, for example, for emissions. If you don't pay any fee for emissions, or you don't have any carbon or NOx bonus, we can select which of the criteria will be disregarded during this contract. Because you can go to the next slide. So during this preparation, we will also define which instrument and which available data will be used to calculate the savings. So we will have, for some of the steps, the fuel consumption, scale, throughput, and emissions. We will have performance, physical evaluation of the performance during the whole project. We'll have different ones. For quality and availability, we will use existing statistics that are usually managed by the steelmaker. Also, based on the production that is processed through the furnace, we will decide what can be considered as a representative production mix to be used for the performance evaluation. And then we define if we need 8 hours, 12 hours, 24 hours of production to be very representative of the total production we have yearly on the furnace. During this preparation step, we will also define the project schedule, because you will see that some of the steps have to be synchronized with furnace outage, maintenance outage. Step 2 is a step that is synchronized with the first maintenance outage after the preparation is over. It's a 5-week site mission to perform the baseline performance evaluation and to apply the immediate improvement, quick win savings. So the idea is, on the first week, we do an evaluation and we build the first line of our dashboard, and we will see what is the specific consumption for the furnace, how much scale is being generated for the furnace, what is the maximum throughput that the furnace can reach with the product mix we are evaluating, and how much emissions we have as the procedure that has been defined, as per the procedure defined during the preparation step. Then we will see what can be improved immediately. And during the week 2, still in production, we will perform all the improvements that can be performed immediately. The third week will be supervision of the maintenance outage. So the customer is doing all the activities that are usually planned during a maintenance outage. And in this project, we have to consider the actions that can be taken during the extra actions that can be taken immediately, according to what has been observed during the week 2. Then we have a 4th week of action that is also synchronized with restarting of the furnace, and we monitor the actions that have been performed and perform some additional improvement. And then on the week 5, we make another evaluation test with as close as possible with the baseline test that has been performed in the first week. And then we can build the second line of the dashboard and seeing where we are now on the 4 criteria that have been evaluated: consumption, scale, throughput, and emissions. Now we will see what is usually performed. This is not an exhaustive list, but the main focus during the quick wins, the first step, the second step, sorry, is burner tuning, the calibration of all instruments, furnace pressure improvement, air-fuel ratio optimization, recuperator evaluation, energy leak tracking, material handling optimization, and maintenance supervision. Out of this list, you will see here a focus on the burner tuning. Burner, for sure, is very important for the reheat furnace. And making sure all the burners are well balanced and that are running as per the design. We can make sure that we are reaching the maximum yield for each burner. So this can have a big impact on the consumption and on the throughput. We can also avoid lean or rich combustion, which can generate scale, NOx if we are too lean, or soot and particles when we are too rich. And it also affects the consumption and the total yield. And we can also make sure that the flame shape is optimal to make sure there is no quality issue on the product. And it can also have an impact on the maintenance cost, because a burner that is tuned correctly will always have a longer lifetime. Another focus is the instrument calibration. During the quick win, step 2, we will make sure that all instruments are working as they are supposed to. Very, very often during this step 2, we can see that some valves are failing. You can see one on the picture. And a hot valve, for example, that is supposed to be closed and is bleeding can drive a lot of hot air, a lot of energy out of the furnace. So this energy is supposed to go in the furnace, but it's going outside. So by calibrating all the instruments and repair the ones that are broken, making sure they are working properly, we can for sure increase the furnace yield. We also control the safety device to make sure the furnace is safe, because sometimes after years we can have safety issues, and the instrument involved in safety can be misbehaving. Few other examples that were on the list. We have the recuperator for burners which are running with hot combustion air. Through my history, seeing all the furnaces everywhere, I have seen many recuperators that had issues. Sometimes they are dirty, sometimes they are leaking, and this for sure can have a significant impact on the furnace yield and the fuel consumption in particular. And we also have an air-fuel ratio optimization to reduce the scale, to make sure the air-fuel ratio in each of the active zone of the furnace is optimized. The furnace pressure is also something that is not always very well managed, because it can be from many regions. It can be calibration of a transmitter, it can be damper issue, but this is also represent very often a lot of money lost. We will track the energy leaks, and we will see if it's possible for the material handling to see if it can be speeded up, or for example, if gap can be reduced to increase the throughput. And like I said, we will do a maintenance supervision to see if we can do some improvement inside of a furnace very quickly that will have a significant impact on the furnace. So after the step 2 is over, most of the time will be 1 year later, there will be a new planned outage for the maintenance on the furnace. And this is when we will perform the third step of the 5-step approach. And this time we will be 4 weeks on site and implement the longer term actions. So we don't do, the reason why the step 2 was 5 weeks and this one is 4 weeks is because we don't do a baseline anymore. The first line of our dashboard was done during the step 2. And now we start, the first week is already implementing the action. So like we have said before, the midterm actions is to perform the actions that were identified during the step 2, but could not be done because there was no opportunity, because we needed some engineering, or because some material was required and we had to wait for the delivery time. The second week will be a maintenance outage supervision. So we will implement the solutions that needed a cold furnace. On the third week, we help restarting the furnace with new elements and continue to perform the improvement. And on the fourth week, we will do a new performance evaluation with the same product mix we have and same duration we have used for the beginning and end of the step 2. And we will see our third line of a dashboard, and we will see how much we have saved on the fuel consumption, on the scale, on the throughput, on emissions, quality, and availability. Again, here we will see few examples of what can be done during the midterms, the step 3 on site. Sometimes on the top right corner, you see that we can reduce the cold air inlet inside of a furnace, because we know that when cold air is going in, we generate locally a lot of scale, and also the cold air need to be to get energy to reach the furnace temperature. So this can be a significant money loss. On the bottom left corner, we see that maybe we had to supply some new instruments because they were broken. So after delivery, we can install them to make sure we have a good control of the process. So it can be a thermocouple or valve or something like this. Repair on the leaks, or also on the bottom right corner, something that we can see very often is a recuperator, which is used to heat the combustion air, but it can be with a lot of dust on it, and maybe cleaning can bring a lot of calorie back to the air and then entering the furnace to reduce the consumption. Then I will turn over to Thierry Robin. We will describe the step 4 with a furnace mathematical model.
Thank you, Mathieu. Thank you for AIST for giving us the opportunity to make this presentation. So I will introduce about step 4, which is the furnace mathematical model step, which the aim is to solve the operational challenges, improve, of course, productivity, respect the quality, which is very important, reduce consumptions, and also scale loss. As it was introduced earlier, in this step 4, it will start among a certain time after step 3 has been done, in order to evaluate at the beginning also some of the elements that permits to be used for the baseline. So globally speaking, we will first start to do basic design, define with the customer what should be put inside of the level 2 in terms of functionalities, specific requirements, way to implement it according to the plant. Once we have defined this, we will engineer the level 2, test it in our local platform, and then we'll come on site in order to commission the level 2 and to finalize with the performance evaluation. One of the challenges is to develop a solution that can work for any kind of reed furnaces, either working beam, working earth, or pushers. Of course, different design means different variation of burner types and position, depending like this, with front burners, side burners, roof burners, or mixed altogether. Of course, it is important to understand the fact that loading variations are different from one side to another. Multiple product types. For long products, you can have billets, balloons, beam blanks, different dimensions, various steel grades, but also different charging and discharging temperature with different temperature requirements. And also some special, very thermal requirements, for example, related to some very significant heating up process that you have to respect some temperature on the surface of the product in separated zones, or limit the temperature variation within the products, different kind of thermal, very specific thermal requirements. The principle of mathematical model should follow this, let's say, basic algorithm, starting from gathering information from different level 1, level 3, and other level 2 system to manage any kind of updates of different events, to be able to perform tracking and pacing inside a furnace, to provide the correct heating curves of all the products within the furnace, to control the furnace dynamically with very specific set points management, and also to be able to adjust actively the pace and to provide heat demand according to the products inside and the requirements. So the level 2 shall be able to build, as I said, according to this algorithm. It's build its product tracking. That can be one furnace, but you can have more than one furnace controlled by the system at the same time, feeding the same meal. Integrate thermal models for all the thermal exchanges inside the furnace. Build online tracking with the thermal profile of all the products all along the furnace. In-furnace pacing model to be able to know when a product enters the zone, how long it will stay, when it will leave. Build optimal heating curves individually per product based on thermal model. Control dynamically and also anticipate zone set points change, because the furnace response is low, but you are moving the product. So it's important also to understand where the furnace is working. Of course, one criteria which is very important because you are not 100% of the time producing, but you also have stoppage, is to be able to manage delay with great efficiency, and also overcome different bottlenecks and provide steady heat demand. So we will see some of these points illustrated, but first we will introduce one thing which is important is what you see from furnace mathematical model is the HMI. It has to provide simple, user-friendly views, which is responsive, give you useful process information. You can see, for example, here, the products inside the furnace, the pace diagram, the temperature evolution of the products, the temperature profile within the furnace, products to be discharged, and different other information, which is also performs easy and quick actions, and also provide the ability to give to different kind of users different kind of actions. For example, engineers will not necessarily do the same as operators. So in terms of technology, the idea is that we will try to illustrate some of the points we have seen earlier. So first, it's important to know everything about your products. So you can track your products within the furnace in real time. And when you click on your products, you get detailed information view with current temperature of the product, what you are aiming, some information about product characteristics or requirements. When you know where are the products, what they are, of course, it is important to model thermically the temperature distribution. And for that, you have to have a precise model of the product. So you will calculate the temperature distribution along the products, all along the furnace, to be able to have a thermal diagram. So in this diagram, you can see, in fact, each bar graph is a product. The blue part is the target end of zone target temperature of the products, and in red is the remaining heat temperature difference you have to reach until you arrive at the end of the zone. You have what we call influence zone, is the way this product, heating this product will influence also the others, because the energy in this zone, when you bring the energy to the others. So they influence each other. On the last diagram here, you see the pacing, globally the remaining time of the products, also displayed in real time. And here in white, the total expected time of the product when it's discharged. You can understand that for this product, there was about a 2 hours delay. And this delay was stopped and then discharged according to this expected residence time. The model, as I said, shall build optimal heating curves. That means dedicated end of zone set temperature of the products to be able to achieve discharging targets, temperature distribution, and other thermal requirements. It is important to mention that this approach is based not on a real online heating curve. That means not pre-computed or read from tables, or doesn't depend on experience plan that will just measure a snapshot of the furnace at a very precise time. So this is completely calculated in real time for all the products. When you know how to heat up the products, you have to control the zones, and for that, you will do that dynamically. According to the end of zone target, you will predict what will be the zone at the end of it. You will know for each product, so take this example of this product here, its current temperature. According to the influence, you will predict the future of the zone temperature evolution according to what you are targeting in terms of product temperature. So the aim of dynamic control is to manage all the zones to heat up all the products according to the end of zones to make sure you achieve all the requirements. In addition, the system also takes into account the ability to control the temperature regarding meal feedback. Temperature from the meal, the rolling temperature, can be used to adjust the discharge temperature and other parameters. In addition, you can also, according to the furnace design, of course, be able to adjust temperature profile distribution of the product in the furnace. At the end, you will also face some delays. So it is important to optimize them and to avoid quality issues. For example, if you go after a delay just too fast, you can bend some products, you can have some issues. So it is important to ramp all the products end of zone during the target by defining, according to the delay time, the right end of zone temperature of the products, and ramp the product has to, in terms of temperature, has to follow to be able to reach at the end of the delay the right temperature to be ready to discharge. Of course, depending on the meal, depending on furnace design, the meal can be the driving force. So it means furnace can be bottleneck or meal can be bottleneck. So it is important with smart active pacing to adjust the way you heat up the products based on which system is bottleneck. Depends on productivity, depends on products, depends on many things. So the active pacing will help you to increase, for example, productivity without affecting the quality. But you are also need for that to be able to achieve stable heat demand. For that, we have fuzzy logic functions that will be able to provide to the level 1 PID settings of the heat demand management to have very stable temperature in the furnace and very stable gas flow distribution all along the control. So these are the different key features of mathematical model that can be implemented into this step 4. Now I will hand over the presentation to my colleague Brenda, who will present you the scale reduction system.
Thank you, Thierry, thank you, Thierry. And then, how everybody. So the first in these steps, the step number 5, we focus on the scale loss. Because we know that in the reheating furnace, the scale loss is one of the critical points for our client. And also that when we work on this topic for the years, we know that for each client, it's quite difficult to use only the standard model to control or to reduce the scale loss. That's why our company tried to, in fact, our company developed a new system is focused on the scale reduction. It's total new system because here that we measure the scale loss by ourselves, by our measuring device on each product. And then all the information will send to the server, and it helps us to build a special model for each client, and we do the communication with the level 2 in order to optimize the parameter for reducing the maximum the scale loss. So on these steps, we will do with the client on site is the erection and calibration of our measuring system. And then we run the system for several weeks in order to set the baseline test with the real and mixed production. And then after we built a special model according to the real information, the data of the furnace, and communicate it to the level 2 system, and do the commissioning in order to set setting correctly all the parameter to get the best performance. So the duration of the steps is around 5 months. and we will work on site with the client to get the performance. And the idea that is we share together the saving for several years. In fact, that this new system that we try to combine our experiments, our company, and also the new technology that we can find on the market for measure the scale loss in real time of all the products. And we built for each client, they have a special process model to adjust the furnace parameter and to control the scale growth in real time. So it has a smart process inside a special server for optimizing the scale loss growth during the process. And then one of the key part of this system is how to measure the scale loss of each product in real time, because we have a rush environment condition. This product is very hot. We work with in a very hot environment. You have the mechanical issue. Yeah, so many water from the descaling machine and also the stream. So we designed a special, we have the special design for doing the measurement under a rush environment condition at a very high temperature. Even the product is over 1,250 degrees. It's okay for us because we have the special thermal protection to protect our sensor or our system. We take into account the radiation emitted by the hot product and also consider the significant difference in thickness between the product and the scale, because the thickness is less than 2 millimeter and the product is over 100 millimeter. So the difference is high, and when we built our measuring device, we take into account all these critical points in order to get the measurement in a very high accuracy. The conception of this system is very simple, but when we see inside the system, it's not very simple, because it have different hardware. We have the camera, we have the sensor with a server, and also different program. Because when we do the measurement, we have a lot of points coming from the product, and also in the same time we collect all the information from level 1, level 2, and level 3. So we have so many data needs to analyze. So we have a physical model, we have the data and image processing model, and we have also the machine learning, because we know that every furnace of each client is different. So we need to build a special model for everyone. And the main result that we can get is the scale mapping, that it can help us to know that it has more scale at the tail or at the middle of the product. And we have also an option to do the automatically calibration, the discharge temperature on the furnace of level 2 system. The scale loss, we can know the scale loss of each product in real time. And also the remaining oxy scale in the furnace, but because one of the main problems of our clients, they need to stop the furnace in order to clean the oxy scale inside the furnace, so that for this system, we also try to minimize the remaining oxy scale in the furnace. And then the last point can give us, we can know that the performance of the furnace, such as consumption and the production. So next is we have different results. This is one of the results is coming from the system. Is in fact we try to scan every product, and after that we can use the result like this to we can know how many percentage of the adherent oxy scale that we can find on the product with the standard or current heating curve. And then after several weeks of learning, we can know which type of the heating curve or which type of the parameter of the process is optimum in order to have only the oxy scale is easy to clean by the scaling machine, but it will not remain in the furnace. So we change, we base on this and change the heating strategy if necessary. The other type of the result is the oxy scale mapping. Because this is, in fact, is the surface inspection. We have a camera that we put at the discharging side of the reheating furnace. From the mapping of oxy scale, we have three main results. The first one is the distribution of not adhering scale on each product. The second one is the temperature. We can know that the head and tail is correctly or not. And also the surface quality, because sometimes we can have, we may have some defects due to the flame of the burner. Sometimes is it coming from the upstream. Some defect is coming from the upstream process. So we can help the client to identify the surface quality. If it have some surface defects, this system can give the information very quickly to our to the operator. So when we get all the results, it means that we can note the heating curve. We note all the parameters of the heat processing, and note towards the scale loss. After that, our model use all this parameter to do the optimization, because we know that the temperature, the resin time, the steel grade of the product, and the hot weight gas. These four points is the critical point for the scale growth. So we tried to optimize all this, do the best compromise of all these parameters, and we propose the optimization to the level 2, and level 2 can adjust the heating curve in order to reduce the maximum the scale growth during the process. We have already test the result of the system on site, and this is one of the example that we can show to you, that we use our system and to change the heating curve of a level 2 in the level 2, and the result is that we can get the saving up to 20% on the scale loss. And then so the main result that we focus, the first part once again is control quality, to detect to find the surface defects from the upstream, and also the defect from the reheating process. It can help the client to do the modification or to do the adjustment as quick as possible in order to get the best quality on the product. And the second part is the oxy scale growth control can reduce the scale up to 30% in the case that we have in the case with the old furnace. and to minimize the adhering scale in order to minimize the oxy scale in the furnace. So this is the main result from our new system of scale reduction system. Yeah. So now I can pass to the next part to my colleague Mathieu.
Thank you, Brenda.
Mm.
So as we explained earlier, the 5-step approach will help you to achieve maximized productivity, efficient energy usage, repeatable and reliable quality, reduced emissions, maximized availability, reduced scale loss, and also important, very good assistance and monitoring with warranted long-term assistance and objective monitoring based on all the performance evaluations we have done for the starting point at the beginning of step 2, and for each step at the end of the step we have objective evaluation based on statistics for some of the items and based on real evaluation, physical evaluation for others. You can see here a summary of of a schedule for different steps. So we have step 1, preparation. Step 2, synchronized with the first maintenance outage. Then step 3, synchronized with the second maintenance outage. Then we have the mathematical model and the scale reduction system. You can see in the orange line that we have different performance evaluations. So on the first part, we evaluate the 4 criteria that can be evaluated during a performance test evaluation with a product mix, with a reference product mix. And we will evaluate at the beginning of step 2, end of step 2 to see how much we have improved, then end of step 3, end of step 4, and end of step 5. For the other criteria that cannot be evaluated during a performance test, quality and availability, we will see the statistics at the beginning of the following step. So we can see where the pointer is now, but we evaluate at the beginning of step 4 the quality and the availability improvement from the actions taken in the step 3. And then the last line, the green one, is showing how we start sharing the savings, because the goal of this is to share the savings between all the partners, depending on the real evaluations of the improvement. So at the beginning of step 2, you will start sharing the savings for throughput, emissions, consumption, and scale. And then at the very beginning of step 3, you will share the savings observed from the actions of step 2 on quality and availability. And then we have the same pattern for the other steps. At the end of step 3, we start sharing on the first criteria. And then at the beginning of the next step, we share for the statistics evaluated criteria. And this until the end. This approach with this schedule. Sorry, can you go back? This schedule is based on our experience. So the 5-step approach was not used, has not been used forever, and but we have built it because we have seen that working with different customers, we have seen that this approach is a good way to maximize the savings by working on every possible actions, like site missions and quick wins actions and midterms improvement, and also mathematical model and oxy scale. On this slide, you can see the proportion of the savings for each criteria expected for each step. It may vary depending on the furnace and also the products you are processing. And for example, if a furnace is not bottleneck, for sure you will not get any savings by increasing the throughput. And we have other examples like this. If you don't pay any fee for emissions, you cannot save money by reducing the emissions. But basically, we can see that for step 2, we will have a big impact on scale, consumption, and emissions. On the midterm site visits, we have again scale, consumption, throughput, quality, emissions, availability improvement. And With the mathematical model, we have scale improvement, consumption, throughput, quality, and availability. And with scale managing system, we have a significant improvement on scale. And the most important on this graph is that we see that after the project is over, at the end of a project, you stop sharing the savings with all the different partners you have worked with during the project, and you can get all the savings for yourself. So these are, I think it can answer one of the questions I have seen in the Q&A. A few examples of the savings we were able to achieve with this approach. The first one is long product furnace, on which we worked in 2020. And we were able to have significant improvement on gas consumption and scale, and also on throughput. Basically, all these savings were reached after only step 2 and 3 by making some improvements. So we went there, measured the oxygen, made a map of the furnace, and we could detect some major issues on the furnace, and we're able to fix them through the process of step 2 and step 3 by making some modification on the water trough and on the burners. Some of the burners were running with a lot of air, for example, and we were able to reach big savings. We have other examples where we were able to give very important savings on the quality for an Indonesian customer. And it's not always the same. This is why we have this 5-step approach on 6 different criteria, because sometimes we can get more savings on the throughput, sometimes we can get more savings on the quality, sometimes on the emissions. It really depends on the furnace, the product, and the history of the furnace. So the main advantages of the 5-step approach, for if we put ourselves in the position of a project manager, is that we have optimized cash flow. You can see on the graph on the right that the cash flow is slightly below 0 until the beginning of step 2, but then start to rise continuously. We can see the few oscillations that are corresponding to the saving sharings. And then we can see that after the end of the contract, when we stop sharing, we have all the benefits for the project manager. We consider that this is a zero risk approach, because all the investment will be done jointly between the steelmaker and any partner that are working with him. And every cent that will be spent on this project will be spent by all the partners, because everybody is paid depending on the savings we can make. So we are sure that we have a real strong team, and that any investment will be made only if we are sure that the return on investment is very, very good. This is also a long-term partnership, because you see that through the different steps, we have a long schedule. And all the partners, again, have to make sure that the savings are very strong and on the long-term basis. And we have continuous monitoring, because everybody has to come on site to do the evaluation and to make sure the savings are consistent over the time. We have a strong supplier commitment, because the supplier will get paid only if he can get very important, significant improvement and sustainable savings. Now, I guess I turn over to Bridget for the questions.
Give me 1 second here. Okay, the first question came in I don't know who wants to take this one. We've got, please describe your experience with reheating furnace for long products. For example, with what steel companies you work for, what strategies have been applied, and what improvement is achieved.
Yeah, I will take this one. So like I said on the one of the slides for the references, the main example, maybe Thierry, you can go back to the slide. This was for a long product furnace, and the actions we have taken there is to go there and for the step 2, the fast actions, immediate actions, we made all the measurement we do everywhere when we come on a new furnace, a furnace we don't know, and we took oxygen measurement, had a look inside of a furnace, and made some evaluations also of the consumption, the specific consumption, studied the history. And the main actions were the quick actions, like I said before, were there was one zone, for example, which was running very lean and was generating a lot of scale on the bottom parts of the long product inside, and also was increasing a lot the consumption. And there were a lot of issues. One of the picture on the presentation which was showing a valve that was broken was also from this plant. So we evaluated all the instruments. We have seen that some of them were broken, some of the instruments were not calibrated properly, and we have taken all this action that we can do immediately when we arrive during the site visit, and we have seen very significant improvements.
Okay, the next question we've got, for scale loss measurement and control, do you still make use of oxygen measurement to understand the atmosphere inside the furnace?
Okay, no, so for this system, we can use in fact, we can use the if I can say that if you have the oxygen analyzer in the correct position in the furnace, and if the information is correct, we can do the control. We can use this to control the air pressure in order to ensure that how to say, to ensure the air pressure and the oxygen contents in the furnace is not too high. But in case that we have we can ensure the oxygen analyzer is have a very well calibration, and also the information coming from, and the position of the oxygen analyzer is good enough.
Okay, thank you. What will the mathematical model for the heating curve be if we make use of regenerative burners, assuming top heating pusher type billet reheat furnace?
I guess this one is for me. The heating curve is really calculated based on the mathematical model. That means this is something you feed, in fact, the model with different tuning settings parameters. And the model, in fact, will generate the heating curve according to the behavior of the furnace itself. And the expected, of course, residence time you will have in the furnace. One point which is very important is that the heating curve calculation starts from the end of the furnace. That means what you are targeting in terms of discharging temperature and global temperature homogeneity within the product. Then the other set points, end of zone temperatures are calculated according to the fact that how you have to reach according to the soaking time. And then basically when you go towards the entrance of the furnace, looking for the minimization of the energy usage, let's say, to heat up the product as late as possible.
Okay. is there any project related to decarbonization, layer reduction, or balloon billet temperature homogeneity improvement?
Yeah, I'll take this one. So one of the action we usually take is to improve the product temperature homogeneity, because this is an action on which we can very often improve the consumption and the throughput, because the discharge temperature is very often defined based on the minimum product temperature, because we need the minimum temperature when the product runs to the mill. And if the profile is not perfect and we have a low point somewhere and we have to increase the total billet temperature to make sure this bottom lowest temperature reach the minimum, we are with balancing. It can be in balancing the burners, putting some topper with different solutions with mathematical model. If we can equalize the profile and have a better profile, we can decrease the average discharge temperature and generate significant savings. This is one of the actions we do quite often.
Okay. Can bar reheat furnaces be evaluated?
Yes, we can do this on reheat furnace, any reheat furnace.
Okay. With the first two steps, could other major combustion appliances be included? Ladle preheaters, EAF burners.
This, like I said, on this approach, this 5-step approach, we jointly all the partners will select only the modifications that are with a very, very fast return on investment. So it can happen that we are discussing big investment, but most of the time it will be small investment with very important projected savings. So usually not big modifications, such like new burners or new recuperator, heat recuperator, or things like this. It's usually all the partners want to maximize the savings because we are all sharing them, and so we make a list during the step 2 of things that can be done, and together we calculate how much saving we can get and how high is the investment, and only select the few items that will generate the biggest savings.
Okay, this next question I'm going to reword a little bit, as we're not really allowed to talk about price in particular during these meetings. It's an off-topic thing, but for a company that wouldn't like a project with a focus on shared savings, is there a different option? And then also, how are you calculating the savings? Many of the slides mention projected savings instead of realized. I guess, what is your definition of projected savings?
For projecting, so the question about the different steps, we don't have to do the sharing all the time. This can be adapted. And about the projected savings is like, for example, if I take the example of the gas consumption, during the performance evaluation, we will do at the beginning of step 2, we will do a real performance test, like maybe 12 hours of production with the real product mix that the furnace is processing during the year, and we will calculate the specific consumption. If we can see that after the end of the step 2 with the same product mix, same duration, same conditions, the specific condition has been decreased by 2% in the exact same conditions, the projected savings that we will have 2% savings over a year, and this will be evaluated at each step during the performance evaluation. So in the preparation step, we have defined how many savings we can expect to get with 1% improvement on the consumption. So this will be the gas cost. We consider 2% of saving on the gas cost, and we start sharing quarterly with the savings we will have in the next 3 months. I don't know if it's clear or not.
Okay. Does the level 2 accurately model beam blank or near net shaped billets?
Yes, this one is for me. Yes, it does. It does any kind of shape of products. For billets, we use the standard size. For beam blanks, we will calculate according to the shape of the beam blanks. So if you have different kind of beam blanks, we use the exact shape of the beam blanks to model the heat transfer within the product.
Okay, so that wouldn't be using like, for example, rectangular equipment. It is the actual shape.
Yeah.
Okay. And this next one is, I didn't see anything in the presentation that mentions training. How will the savings be sustained if training of local personnel is not part of the process? Does the project include training? My experience is if you don't train the people, old habits and misperceptions will continue.
So there is no special training for this, but for sure, every time we come on site and do the modification together, we will, this is part of practical training, and we will, for example, we also have, all the partners have to make sure that the performance will be sustainable, because we are not evaluating the benefits of step 2 only at the end of step 2. We have to make sure they will still be there for step 3, sorry, step 4, for every steps. So there is no classroom training, but let's say the hands-on training will be every day we are on site, because we have to make sure the improvement will be sustainable.
Okay. And do you have any focus on process stability? Keeping a constant billet temperature is more important to us than energy savings. If the temperature is stable, the rolling process is stable. We are a rolling mill, and rolling stability is the most important factor. We have our own mills focus on energy savings, and this leads to higher roll wear and less stable rolling. We also have had mills that run as fast as possible, which means they outpace the furnace, and thus the billet temperature is not stable.
Yes, the process stability is something that we definitely work on, and the savings evaluation we can see on the availability, which is one of the 6 criteria. If this can also, we didn't give an example during the presentation, but this can also generate a lot of savings when we reduce the line outages that are due to the reheat furnace. So when we see that we have a lot of mill unplanned outage due to the unstable billet temperature, for sure this is one of the items we will focus very carefully, because we know that this can bring to all the partners a lot of savings.
Okay.
And this is mainly through the level 2.
Got it. Okay, and then there's 3 questions here that were actually answered via text. It might be useful for the group. I'll just go through them real quick. So they want to know if this can be done on any OEM equipment, and does it matter if there's an existing level 2? And Mathieu answered, it can be done on any OEM equipment with or without level 2. Actions will be different if you own a level 2 that can be modified, but very often the solution will be to replace an existing level 2. This next question was for Brenda, and asking, am I right to say the scale loss monitor is only used for initial mathematical heating curve adjustment and not used for the continuous production for the long term? Brenda answered, it uses for continuous production for the long term because the system has a program to collect all data from levels 1, 2, and 3 and to revise automatically the heat strategy according to the real mixed production on site. And then the last question I have here, again for Brenda, what is the way in which the dew point of the environment would affect the scale properties, adherence, uniformity, and growth? The percent of water content in the hot waste gas has an impact on the adherence of oxide scale. And let me just go here. And looks like we're done. Final question here. It says, how do we get more information to follow up? Looks like there is email addresses here on the screen for contacts for the presenters. Ken, I'll let you take over now.
Thank you, Bridget. Get my video back on. Well, thank you, each of the presenters. You guys did a terrific job. Try to get my screen up here. Which way did it go? I apologize, it's gone bye-bye. Thank you for presenting. You guys did a great job. Very informative. Bridget, thank you for being the moderator on this. This concludes the webinar. I thank all of our attendees for joining us, and our next webinar will be in, it's right here, March 4th with iSend, improving periodic defect detection in hot rolled long products by means of combination between eddy current and vision systems. So again, that's March 4th, 11 a.m. Eastern will be the next webinar. And with that, that's it. That's the end. Thank you.
Thank you.
Thanks, Ken. Thanks, everyone.
Thank you very much.